All right. The couple of announcements I mean to make before we get started today, and sorry we are starting late because I had that phone call come in right as I was trying to grab something to eat. First, I apologize if any of you showed up, came and didn't get to hear. There could be, and I'm hoping not, but I think I told you last week that I've been assigned to be on a screening selection committee for a biology instructor, and it took just about all my office hours last week screening applications, and I got them done over the weekend and sent them on back to the Birmingham campus, so they're on the way. But at some point, they're going to schedule some interviews, and hopefully we can get them all done in one day, or if they do them on 2 days, hopefully they'll do them either 1 day or 2 days on Tuesday or Thursday. Whether they do that or not, I'm not sure. I've told them repeatedly I'm stacked from 8 o'clock in the morning till 9 o'clock at night with classes and don't have more than 20 minutes anytime in between. So please schedule for Tuesday, Thursday. That means they'll probably schedule for Monday, Wednesday. Now, already we have missed 3 Mondays, okay? Memorial Day, when I had to be at the meetings in New Orleans, and then last Monday was an unexpected one. So now what it was a 10-week course is now an 8.5-week course. So sorry about that. We'll do all we can to catch up and get as much covered as you need. In a full-term course like you'll be in, there won't be likely that many days will be missed. But this has been crazy this summer.
Do you know which week we're on right now?
What's that?
Do you know which week we're on right now?
What week we're on? This is let's see, 1, 2, this beginning of the 6th week, I think. Yeah, so we're just over midterm, just past midterm. Last Thursday started midterm. This day is the first day of the second half of the term. Okay, is that a master's hat? Good deal. All right. Okay. So there is a chance I'll miss another class if they schedule interviews that day. I'm hoping not. Okay. It seems like there was one other thing I was going to say with that, but I can't remember what it is now. So we'll go on. Any questions on anything we've covered so far? Okay, we are recording, so let's move on to now. Section 5.6 says systems and energy conservation, and we've really hit most of these points already. What we haven't hit is what they call the non-conservative forces with energy considerations. The previous slide was conservation of energy with the spring, which we covered in 5.5, spring potential energy. And I think we've hit most of the others, but let's pick up. And I'll add a few things here that are not showing up on the slides here. I'll try to list it where they are here. Recall the work energy theorem can be written this way. Now this is not exactly this slide, but this slide picks up a little bit later. The work from non-conservative forces plus the work from conservative forces, of course, is your change of kinetic energy if you're dealing with energy of motion. Okay? What this is saying is, remember what's the formula for kinetic energy? Anyone remember? I know it's a long break. Kinetic energy. Half. Okay. What do we mean by kinetic energy? What is the meaning for that? Energy of motion. And if you're moving, what do you guarantee you got to have? If you're moving, you've got a second word. Okay, there could be work involved, but what characteristic of motion? you're moving, you've got a
Displacement.
that's for sure. And what's the first derivative of displacement? What's the time rate of change of displacement?
Speed.
Yes, speed or velocity. So velocity is going to be in kinetic energy. So I ask again, what is kinetic energy? It's got V in it. And it has a 1/2 in it. I gave that away. How much of there is there of mass? 1/2 mv squared. That's your kinetic energy. And if you have a change of kinetic energy, you're either adding work, you're doing work on the system, that could be conservative or non-conservative, or if the ball is just flying through the air and it's changing its kinetic energy, that means that either the system is doing work on it, either conservative or non-conservative. Give me an example of conservative change of kinetic energy. What work would you be doing? Yeah, if I throw the ball up, I'm doing work against what? Gravity. That's conservative because on the way down, it'll pick up that energy, right? So that's conservative work. But as it's going up, it's hitting air resistance. Any frictional or resistant type force like that is a non-conservative. So your non-conservative plus your conservative will give you your change of kinetic energy. Okay? That's the first little formula they have here. Now, breaking that down into another one, this is all on page 142 in the new edition, wherever that is in the old one. The non-conservative work, my printing is really pathetic, would be, I went to write an equal sign and wrote a plus sign. Sorry. Okay. Your change of kinetic energy plus your change of potential energy. Now, if that were conservative force, okay, this sum would be 0. If everything was conservative, whatever you gained in or lost in kinetic energy, you gained in potential. Or whatever you lost in potential, you gained in this. So those changes would go to 0. If they're not 0, then that accounts for that non-conservative work that was done. Okay? Now, if you break those down, your kinetic energy, change of kinetic energy, remember delta means what? Difference in, okay? So, and the difference is always measured as difference between what? Final minus initial. KE final minus KE initial. That would be the change of kinetic energy plus, what would it be for potential? PE final minus PE initial. Again, my writing stinks. Okay, so that would be the non-conservative force would be your unaccounted for change of kinetic and change of potential energy. Okay, now another way to write that, if you combine these two together, that would be KE plus PE F minus, I've been writing a little F, KE plus PE initial. Okay, that's another way to write it. They wrote it within the parentheses, which is fine. Okay, but that's the other way. And basically what this is what is the sum of kinetic and potential energy? Another form of energy, talked about a few slides ago. It's quite a few slides ago. I'm trying to find it now. There it is. Mechanical energy, the sum of your kinetic and potential energies. So basically what this slide is saying then is that your non-conservative work done by the non-conservative forces would be your change of energies. Change of mechanical energy final minus mechanical energy initial. Okay? So there's that. That's your equation 521 at the bottom of page 142. Okay? And if you weren't just limited to mechanical energy, then you would say that non-conservative forces would be energy final minus energy initial. Because guess what? Total energy is conserved. You can't lose it. It goes in different forms. However, if there is an apparent loss of energy, that meant you did work on the system. Non-conservative work. Okay. Now, you could call that delta E2. I'm trying to keep up with the formulas the book is giving that are not on the slide set. Okay. Now, they also do a little bit of description here, and I'm not going to write this down because I don't have room to write it. What is work, especially in the mechanical energy sense? Basically, work in this topic transfers energy to a system by displacing it with an applied force. Now, that's sort of a weird definition to it, but work is basically using energy, okay, to change a system, to change its elevation, to change its speed. Whatever you're doing to change a system, that's work, okay? Now, the work can be done by the system or the work can be done on the system, either one, okay? That's what work is. Heat. Heat is one form of change of energy. If you rub your hands together really fast, holding them together, you'll find they get hot. Why in the world do they get hot? Because of friction between your hands there. Heat is the process of transferring energy through microscopic collisions between atoms and molecules. Okay? In other words, if you're doing this, what you're doing, what produces heat, is on the almost molecular level, or cellular level, you're having friction, and every time you do, that adds some heat, and you complete that. Okay, mechanical waves. Okay? When you were a kid, and the hose was stretched out there across the grass, did you ever pick up one end of the hose and sling it down? What happened? You see that wave that you produce by that motion like this move down the hose, right? That would be a mechanical wave. When I'm talking to you, I'm compressing air molecules. That's what makes the sound. And these air molecules, compression and rarefactions, that's what's transmitting the sound across the room you're picking up with your eardrums. That is what they mean by mechanical waves. Transfer energy by creating a disturbance that propagates through air or through some other medium. Okay? Your stereo system, all these things, any speaker you have, microphones, they're using mechanical waves. Electrical transmissions, okay? Let's take that telephone. As you speak into it, you're creating mechanical waves. That's what's compression rarefactions. They're changing, and we'll get to this in the next course, electromagnetic fields, and that's producing electric current. So that's electrical transmission. And electromagnetic radiation would be like what's happening on the sun, the heat that's coming to us, the light that's coming to us, all those things are electromagnetic radiation. So that was 5.6. 5.6.1, conservation of energy in general. Now, we've already said this several times. The most important feature of energy approach is the idea that energy is conserved. It cannot be created. It cannot be destroyed. Energy, total energy, is always conserved. It's called the conservation of energy. Okay? Let's do quick quiz 5.8. Now, I don't know if your editions have that, but the new edition does. A book of mass M, okay, is projected. I'm going to throw it across the room to Courtney there. Okay, you ready? Okay, good. Okay. Is projected with a speed v. Oops, this is across a horizontal table. So this desk, I'm going to slide this across the desk. The book slides until it stops due to a frictional force between the book and the surface. You can imagine that. I mean, it doesn't have to be a book. Let's just have this. I slide that, and indeed, well, I can't keep it from turning over. I slide it this way. It does stop. Why does it stop? Because of friction between the top of this and the desk. And that's a rough old desk, okay? So, the book, until it stops due to a frictional force between the book and the surface. The surface is now tilted at 30 degrees, and the book is projected up the surface with the same initial speed v. When the book has come to rest, how does the decrease in mechanical energy of the book-earth system compare to that when the book slid horizontally? Okay, again the question. When the book comes to rest, how does the decrease in mechanical energy of the book-earth system compare with that when the book slid over a horizontal surface? A, it's the same. B, it's larger on the tilted surface. C, it's smaller on the tilted surface. D, more information is needed. Okay, we're asking about when the book comes to rest, how does the decrease in mechanical energy of the book-earth system compare to that when it slid horizontally? Any ideas? A, it's the same. B, is larger on the tilted surface. C, it's smaller on the tilted surface. D, more information is necessary. And it's the book Earth system. Now, looking at the formulas we just talked about, on the horizontal surface, what's the only energy change? Say again? Okay. I couldn't hear you, a little louder. Okay, yeah, now friction is making it stop. But what were the energy involved? The work done on friction, absolutely. What was the other energy change? Because the work done by friction has to be one or the other, kinetic or potential. Say again? Kinetic, because on a horizontal surface, there is no change of potential energy. It's all kinetic. And the work done, the non-conservative work, was due to the friction. Okay, how about going up the incline, the tilted surface, 30 degrees? What kind of energy changes are happening there? Say again? Yes, you have a potential energy change as well as a kinetic energy change. Kinetic energy change is the same. Potential energy change is greater. That means the work due to friction had to be less. So that would be smaller on the tilted surface. Okay? Does that make sense? Okay, this is... Say again? Yeah. Okay. Just got to find you. There you are. Okay, good deal. Okay. So that would be less on the surface like this, because change of kinetic energy is the same, change of potential energy greater. That means the work done by friction was actually less. Okay. All right. Let's just go to the rest of this slide, which, okay. I'm sorry, this is the slide from the last section. This is where I should have been writing that. When non-conservative forces are present, the total mechanical energy of the system is not constant. When non-conservative forces are present, the total mechanical energy is not constant. Just like that example we just gave. When friction is involved, yeah, you don't have conservation of mechanical energy. The work done by all non-conservative forces acting on parts of the system equals the change of mechanical energy of the system. And that's exactly that same last slide I had here. The non-conservative forces here is the change of mechanical energy, total change of energy. Okay? So the non-conservative force is your change of energy. You haven't lost any energy, but energy input, energy output, initial, final, they're different, but you haven't created nor destroyed it. You did non-conservative work that you'll never get back. Friction produces heat that's wasted, lost in space. Okay? Here are those equations I just did before. Sorry, I was looking at the next slide. Those are exactly the same two equations I did before. That non-conservative forces is change of potential, kinetic energy plus change of potential, or if you combine the finals together. And the way they've written this is backwards. Okay, this should be final here, initial there. This slide they got it backwards. But everything else is correct. The energy can either cross a boundary or the energy is transformed into a form of non-mechanical energy such as thermal energy. Friction, work. Okay? If positive work is done on the system, the energy is transferred from the environment to the system. If positive work is done on the system, okay? Let's say at the Masters Golf Tournament, the ball is set up there on the tee, okay? And it's just sitting there. How do I get that to change energy? I give work to the system. Do work on the ball, and if positive work is done on the system, energy is transferred from the environment to the system. If negative work is done on the system, once that ball's in flight, now it meets air resistance, especially if you hit it really hard. Now energy is transferred from the system to the environment, and you're actually, believe it or not, heating up the air right around where that ball flies, okay? Increasing its kinetic energy of the air molecules, okay? I think I just lost my place. I don't know how I did that, but okay. Now, how do we transfer energy? And this is basically saying the same thing the last slide did. By work. Applying a force, you hit a force on the ball, it takes off and goes. Produces a displacement of the system. The ball was at rest, now it's flying through the air. Heat, the process of transferring energy by microscopic collisions between the atoms or molecules. The ball is running into the air molecules and increasing their kinetic energy, which technically increases their heat. We haven't gotten there yet, but we'll talk about that later. For example, when a spoon rests in a cup of coffee, you probably experienced this before. You pour that boiling hot water, McDonald's coffee, put a metal spoon in it, grab that spoon a little bit later, what do you notice about the spoon? It's hot. And why? Because the heat is on a microscopic level. The coffee is very hot. Those molecules are moving rapidly. The metal, fairly cool when you put it in there, but now those molecules start moving rapidly, and they move on up the handle of the spoon, and soon it becomes hot. You've witnessed that on the stove before too, I bet, when if you're using a metal spoon to stir something, you forget and leave it in the pot, you go to pick up that spoon later, very hot, okay? Because some of the kinetic energy from the molecules in the coffee or the pot or whatever transferred to the molecules in the spoon as increase of internal energy, which is what we call heat. Mechanical waves, I just went through these. Any disturbance that propagates through a medium, sound, water, seismic, flicking a hose, all those. Electrical transmission, transfer by means of electrical current. That's how energy enters electrical device. The electrical energy is coming in here. We're not using the electrons. We're using the energy the electrons have. It's all an energy process, okay? You're not using up charge, you're using the energy of the charge. Electromagnetic radiation, I mentioned that before. Any form of electromagnetic waves, light, microwaves, radio waves, any waves that you have that you can't see but are electromagnetic. Microwave oven, that's how you cook that. Microwaves go through the materials and actually excite the water molecules or the fat molecules. Those are the main things that are excited when you're heating in a microwave. That's why stuff like rice, you can't cook rice easily in a microwave because rice is hard, just almost totally starch material. It doesn't really get excited, okay, when you do it. Anything with moisture in it, if you cook it in water, yeah, you'll do it, but basically you're boiling water and that you're cooking the rice. Okay, light energy traveling from the sun to the earth, I gave that very example. You can neither create nor destroy energy. Another way of saying energy is conserved. If the total energy of the system does not remain constant, the energy must have crossed the boundary by some mechanism. In other words, okay, what's your name, please? Amber, got it. Now finding you is the hard part. There you are. Got it. Okay. Let's go back to the ball on the tee at the Augusta National Golf Course, okay? Just sitting there. The system is in equilibrium. Nothing's happening. You have to have an external force come in and move it. The energy must have crossed the boundary and entered that system to give that ball, get it to move. It could be wind blowing it off the tee, and that would work. It applies to areas other than physics, of course, in all kinds of areas. Chemistry, they even have the same type of thing in things like economics and stuff. Now we're ready for 5.7. Okay, on the slide it said 5.6, but in your text this is 5.7. Let's go back to when we first started the course. And someone mentioned already today displacement. Displacement, you were here, you wound up there. That's a displacement. Once we measured a displacement, talked about the displacement, what other feature could we get from that displacement? Same one we mentioned before. Velocity. How is velocity related to displacement? The time rate of change of displacement is velocity. Okay, then we got velocity down pat. And guess what we did to it? Time rate of change of velocity is acceleration. You do that in your car. If you change your velocity, you're accelerating. Either by pressing that gas pedal down, going faster, or by hitting the brakes, slowing down. Or even by turning the wheel, which changes the velocity being a vector quantity. Okay, time rate of change of velocity is acceleration. Well, when we're dealing with energy, guess what? I'm trying to remember, did we do momentum yet, or is that still to come? I think that's still to come. I'm teaching 6 different courses, and No, that's the next topic. Okay, so we won't use that today. When we're dealing with energy, guess what we do? We got energy down, then that's what we're going to do. Time rate of change of energy is what? Power. Often, also interested in the rate at which the energy transfer is taking place. That's how we define power. Power is not the same as force. It's not the same as energy. It's the time rate of change of energy. Power is defined as the rate at which energy is transferred. So this is average power is the change of work or the amount of work done over a time period. That would be your force times your average change of your velocity. Okay? Now, I don't know if you pictured that as being the same thing. That doesn't sound like it has anything to do with each other, with themselves, does it? Well, let's see. What would be the units for power? Let's take work. What's the units for work? Joule, okay. And time? Second. So joule per second is a, what would you call power? What would be the unit for that? What? Watt, yeah, okay, never mind, okay. That would be a watt, okay. Capital W, why capital W? Named after James Watt, Scottish engineer who defined what horsepower is. He didn't use metric, he used English, okay. Let's see, what is a joule though? Remind me of that. Say again? Yeah, it's work, but what would be its fundamental units? Kilogram, meter squared, per second squared. You got it. Now, what would be a force? A Newton, which is a kilogram, meter, second squared. Yeah, force times acceleration. Multiply that by velocity. What's the velocity? Meter per second. Okay. And this would give you kilogram meter squared per second squared per second. Okay. That's exactly the same unit. Actually, we don't usually say this, but kilogram meter squared per second cubed. Since you divided by, again, but it's change of energy for change of time. So kilogram meter squared per second squared per second. Kilogram meter squared per second squared per second. So it is the same. Force times your velocity, average velocity. The SI unit for power of watts. Joule per second is a, they've got it wrong. Sorry about that. They should have, if they write it this way, that should be second cubed, not squared. Okay? Do they have it right in the book? Do they even say it? Yeah, they do say it in the book. Your equation 526, you see that is per second cubed, not per second squared. So they had it wrong on the slide. Sorry about that. And then their tip, what's the difference? That's, again, play on words. Don't confuse the non-italic symbol for watts, which is W, for the italicized symbol W for work. Capital W as a unit is a watt. Capital W as a parameter is work. Different things, okay? So don't confuse them. I can't write in italics, so therefore you have to read it by context. In the book, though, if it's italicized like this, that's work. This should be non-italicized, which to me looks exactly the same. This is non-italicized. This one should be non-italicized, just like that, joule per second. Okay. So they broke their own rule right there. Watt is a unit. Work is a parameter. Okay. Work is a concept, but it's units for joules. Okay, any questions? Power. Before we get into instantaneous power, let me give you a dumb example. Okay, in fact, I don't even see. where the book is even mentioning instantaneous power. Interesting. Let me give you a dumb example. Did I start the story ever about digging the patio in our backyard? Okay, I started that. Okay. Now, when I was digging the patio in our backyard, we had just moved into this house, and I wanted to get the water pressure off the back wall. Some previous owner had built an extension on the back, but the water went right against that. I wanted to get that hydraulic pressure off the back wall, also get the earth down so it wouldn't have wood to ground contact, so there wouldn't be termite problems. So I was planning just a little berm and that kind of stuff. My wife said, good, I wanted a patio anyway. Not exactly what I had in mind, okay? So that summer I started digging on that. Now I dug for about, I'm just going to estimate, 5 to 6 weeks, okay? Every day that wasn't raining, I was praying for rain that summer. It was a dry summer. Okay, so just about every day I was out there digging, a pick, a shovel, and a wheelbarrow, and moving soil. Okay, I think I did tell you this because I hit the rock, and as long as I wasn't moving the rock, no matter how much I sweated and grunted and everything else, I was doing no work. Because work is force times the displacement. If I didn't displace it, believe it or not, I was doing no work. Okay, but I worked for about 5 to 6 weeks moving that soil, getting it out of there, and I got about half the patio done. Also ran into so many rocks and stuff. Well, it got to be Labor Day weekend. I was coming back to work the next Tuesday or Wednesday. No way I was going to finish that. No way I was going to have that much time off again. We said, we've got to do something. Well, the reason I started digging, rather than hiring someone to dig, there was no room to get a bobcat in there to operate. But by the time I got half the patio dug, there was room now for a bobcat. So we started calling around, and I guess my wife found a bobcat service, and we come out, and it seemed like it may have been a Saturday, or it may have been Labor Day itself. I don't remember which. But they said they would come out, and he brought this big old honker of a bobcat, and in basically a little over half a day, he did the other half of the thing. Now, what was the difference? I moved half the soil in 5 weeks. He moved half the soil in a little more than half a day. Who did the most work? We did the same amount of work. I moved half the soil, he moved half the soil. What was the difference in that situation? The time. And what is time involved with? Power. Work per unit time. That bobcat had considerably more power than I did. At my best, I'm probably well less than half a horsepower, more like a quarter horsepower. That bobcat was out there probably with 300 and some odd horsepower. I don't know. But it had a lot more power than I did, okay? So he could get the same amount of work done in a small fraction of the time. Now, I admit, he just piled it on the edge. I still had to move it. And I was moving it the whole time, so I did a little bit more than him. But the power was not. Now, let's look at instantaneous power. As we said before, this formula here, average power is equal to force times average velocity. Okay? For instantaneous power, that would just be force times velocity at an instant. Okay? Now, both the force and the velocity must be parallel to each other. In other words, remember, force is a what kind of quantity? That has a direction? Vector quantity. Velocity is what kind of quantity? Vector quantity. So force times velocity, both in the same direction, that gives you power. Okay? Now we ran into this in work as well. Force times the displacement, that was work, both vector quantities, but that was what we call a dot product. Now, we're not going that deep into this, but when you multiply two vectors together with a dot product, you get a scalar. So power, just like work, is a scalar quantity. But the force and velocity must be parallel to each other, and they can change with time. Force can be time dependent, and velocity, of course, is time dependent, or can be. Okay? So instantaneously, whatever the instantaneous force times the instantaneous velocity, that's your power at that moment. So let's look at the other power units. What was it in the metric system? Power is measured in what? Watts. Okay, very good. In the U.S. customary, generally horsepower. I already mentioned that. Okay. You need a conversion factor. Okay, here's the one. We'll be using this in the lab. If we don't get it done today, we'll be doing it next time. 1 horsepower is 550. Now, the units for work in the U.S. customary system, force times displacement. What's the unit for force? U.S. customary. Stand on the scales. Pounds. And distance. U.S. customary. Foot. Foot pounds. That's work divided by second. That would be foot pounds per second. There is the short version. But if you have 550 foot-pounds per second, that's called 1 horsepower. 550 foot-pounds per second is 1 horsepower. Now, just to give you a general idea, a watt is a very small amount of power. Okay? It takes 746 watts to make 1 horsepower. Horsepower is a pretty good size. A watt, pretty small. Very small. But quite often we don't use watts. We use the decimal 3 places in what you have. Make the number smaller, make the unit bigger. 3 places. 1,000 means metric. 1,000 meters would be a 1,000 grams would be a kilogram. Okay, kilos. So we use kilowatts. 746.746 kilowatts is 1 horsepower. So a kilowatt is a little bit larger, but they're equivalent with horsepower. Very close. About 3/4 of a kilowatt is 1 horsepower. Okay, close. You can define units of work or energy in terms of power. Well, how can you do that? Work or energy in terms of power. Let's go back to the first definition we had. Power is equal work over time. How can you solve that for work? What would you do? Multiply both sides of the equation by time. So power times time is equal to work or energy. Okay? So you can define work in terms of units of power. For instance, on your electrical bill, what are you paying for? You're paying for energy. You're not paying for power. Even though you call it a power bill, you're not paying for power. If you'll notice the units, show the units on your bill, it's going to be kilowatt hours. Kilowatt measures power times time in hours, you get energy. That's the energy you use. Kilowatt hours is the energy you've used, and that's what you pay for. It's a unit of energy, not of power. Kilowatt, that's the unit of power. Kilowatt hour is the unit of energy. Make sense? Okay. Now, jumping another rabbit here, pretty quickly here. This is in your text is 5.7.1. On here it's still part of 5.6. It's center of mass. Okay? The definition's on the top of page 148, but here it is in the slide set. The point in the body at which all the mass may be considered to be concentrated is the center of mass. Okay? even though you may be a long, gangly something, your center of mass is somewhere. Okay? When using mechanical energy, the change in potential energy is related not to how far your head moves, how far your knees move, your feet move, it's how far your center of mass changes. The change in potential energy is related to the change in height of the center of mass. Okay? Now, people use this for in all sorts of nifty ways. If you ever watched, now this shows how old I am. Well, it doesn't quite show that much, but it does a little bit. The videos of Michael Jordan when he was jumping. I mean, he was not that tall. What, 5'6", 5'5"? I mean, 6'5" or 6'6", something like that. What do you think?
6'6".
6'6". Okay, 6'6". And yet he could dunk a ball like crazy. Michael Jordan used his center of mass better than just about anyone else I can imagine. I'm sorry? Monique, yeah, okay, I was just trying to find you. I know you're in here, there you are. And? I'm sorry? Brad, yeah, here. Okay, good deal, thank you. Okay, because what Michael Jordan did really well is he would bring his feet up, making his center of mass higher. So, and the center of mass was what was moving, so he actually did it. It's just incredible how he could do what he did. It still seems sort of close to impossible. So, another example. Let's see. Aren't the Winter Olympics coming up this year? No, next year, 2018. Pretty sure they are. Winter Olympics are not divisible by 4 even years, and the Summer Olympics, when they are divisible by 4 even years. Have you ever watched the ice skating pros? Okay? When they start their spins, if they start to spin like this, they go fairly slowly. But if they pull their arms in, they go like a top. I mean, they spin so fast. And that all has to do with where the center of mass is. Okay? So it's a strange example of it, but it is. The change of potential energy, is related to that change of the height of the center of mass. All right. And that's all they say. In the text, there's a bit more done, so please read the text. Again, we have already lost now 3 days out of the 20 this summer, so we can't do everything that's in the text. We're moving on to 5.8, which is on the slide set 5.7, but in your text 5.8. Work done by varying forces. Okay? A constant force would just be a push. A constant shift, push or pull, something like that. However, we've talked about one variable force already. Do you remember what that was? Spring force. Because the more you want to stretch it or compress it, I don't care. Stretch it, okay? If this is a spring at equilibrium, if I pull a little bit, the spring's going to pull back on me a little bit. If I can extend it more, it's going to pull back harder. That is a variable force. The greater the displacement, the greater the force. You have to do as well. So the work done by a variable force acting on an object that undergoes a displacement is equal to the area under the graph of f of x, which is the x component of the force, versus how far it's displaced. Okay? And Ryan decided to come today. That's good. Okay. All right. Now, have any of you had calculus? Okay. What, when you start talking about calculating areas, what are you doing? Did you have, huh?
What do you mean?
What calculus operation were you doing? Are you in Cal 1 or Cal 2?
I was in Cal 1.
Oh, Cal 1? Okay. When you're doing area under a curve, you're talking about integration. Now, we're not going to be integrating because this is only trig-based, okay? But what you're doing is estimating the area under a curve. integral calculus is, by the way. So the work done by a force is estimating the work under the F sub x, the component of the force in the direction of your displacement, times the change of displacement. The area of the curve exactly equal to work done by the force on the particle during that displacement from x1 to xl. Initial displacement to final displacement, and that's your force. Notice it's a variable force. It started small, got bigger, and then decreased a little bit toward the end. A variable force, but the work done was the total area under that curve between those two displacements. Spring is one example of that. If you remember your formula, whose law was this? Hooke's law, okay? Hooke's law said that the applied force is your Hooke's constant, or your spring constant, times your displacement. So the greater the displacement, the greater the applied force. The smaller the displacement, the lesser. So it's a variable force. But that was varying in a linear sense. X is just to the first power here. So that means you have a straight line force. Your force applied is proportional, and the constant proportional is that spring constant. However, when you do the area under that curve, let's think of that. The area under this curve would be the base times the height, right? 1/2 of that, right? Area of a triangle is 1/2 the base times the height. Well, the base here is your 0 to x max, so that's your delta x, okay? And the point here, that's your force, kx. And you have 1/2 of that, so 1/2 the base, x, times the height, kx, 1/2 kx squared. Now that's the maximum, that's the work you got to the maximum that you happen to extend that spring. So if the process of moving the block is carried out very slowly, the applied force is equal to the magnitude of the in opposite directions of the spring force at all times, so your applied force is exactly equal to the spring force backward, which is what this says, and that is equal to the work done is the area under that curve, and since that's a straight line, that area would be a triangle, 1/2 kx squared. Kx is the force, x is the displacement. Okay? Does that make sense? Now that works for this one. It also works for this one, even though that's a variable force with a lot stranger variation than this one is. So that formula still holds. The work is also equal to the area under the curve, which we just talked about. In this case, the curve is the triangle here. The area of that triangle is 1/2. There's your 1/2. The base, which is your x, and then the height, which is kx. So 1/2 kx squared. Okay? Now, I hate it that they put the 1/2 here and the kx squared here, the kx squared here. You ought to have the kx squared there, or the 1/2 down here, one or the other, but don't split it up like that. Okay, does that make sense? So the work from a spring is 1/2 kx squared. Whoa. That is, folks, the last slide in the section. Okay, there's an interesting little blurb here at the top of page 149. The maximum power output from humans on various periods. Okay, I said when I was digging the patio, I doubt if I got much more than, I don't even think close to 1/2 horsepower, more like 1/4 or less, maybe 1/10. Here's what they say in this table. If you do something for a very short period of time, just put everything you got into it, you can get up to 2 horsepower, okay, or 1,500 watts over a 6-second time interval. If you increase it to 60 seconds or a minute, you may be able to maintain 1 horsepower or 750 watts. For 35 minutes, where they come up with this, I'm not sure, is 0.35 horsepower or 260 watts. For 5 hours, 0.2 horsepower, 150 watts. 8 hours, which is what I was trying to do a day, barely a tenth of a horsepower or 75 watts. Those are the safe daily levels, and I tried to be safe. Okay, and all I did. Okay. That ends chapter 5, and I think we have time for the lab, so we're going to do the lab next. I'll see if I've got the test run out. If I haven't, I'll get it run off while you're doing the labs. But before we get there that far, the end of every chapter, there is a summary. I'd say nothing replaces reading the text. Like I said, we're covering ground faster than we have time to, so try to read the text. The summary summarizes the important issues in it, most of your important equations, but if you'll notice, they don't even do them all. I see 5.3, 5.6, 5.7, so they don't have them all listed here, but they list most of them. The conceptual questions, well worth your look. There on page 153 and top of 154. I think those have odd number answers in the back. And then the problems, and again, the odd number answers are in the back. 5.1 covers odds 1 through 7. 5.2, 9 through 17. 5.3, 4, and 5, those three sections together cover questions 19 through 31. 5.6, 33 through, 49. And then 5.7, power, that's covered in problems 51 through 57. Work done by varying forces, 59 and 61. And then you have some additional problems here which mix all of those different sections together, and you can do any of those 63 through 85. Quite a few of those. All right, that's where we'll stop today. And I'll discard that. If you want to take a little break now, you can, but before you do, let me check and see if, I can't remember, last week was such a blur because I was doing all that screening. I can't remember if she ran off copies of the lab for me or not. Let me check and see. Oh. This would be okay. No, I don't have a runoff yet. Okay, let's do the lab on power. I have one lab on energy, which is fairly short, but I think you get to do more on the power lab, so let's do the power lab. Now what I've got to do is run down and get that run off, so I have it in my office. I don't have it up here with me. So if you need to take a quick break, let's see. No, we go till 3:30. Let's get started. I'm sorry. I was looking at my clock for a watch on. Let's get started on chapter 6, or topic 6. We're supposed to go till 3:30, not 3. I was thinking. So, see, I was about to cheat you out of some of your tuition dollars. I apologize for that. That was the last thing I ever would want to do. Okay. So let me get back to this. That's all you want to take in today. Okay. Absolutely. Glad you could come. So let's get started in topic 6, because like I say, we already lost so much time, we can't really afford to lose much more. And we get, there it is. Does anyone else come in since I called roll? Okay. All right. It's called Chapter 6 in the slide. It's Topic 6 in your new edition. Okay, we will start from the current slide. Now, your Topic 6 in your new book, which I like the title better, is Momentum, Impulse, and Collisions. The old edition called it just Momentum and Collisions, but they did impulse too, they just didn't have that as part of the topic. So, let's get a few definitions first. Now, why they start with collisions, I don't know. Later we'll get to momentum and impulse, and we'll get there. That's where your book actually begins. Conservation momentum, by the way, is another one of your conservation principles. It's sort of fixing our minds things that have been conserved so far. Generally, we conserve mass to be conserved. Generally, we conserve energy to be conserved. The problem with energy is energy changes form so easily, so quickly, so seamlessly, you don't even know it's going on sometimes. But total energy is conserved. Momentum, though, is a little easier to measure, and that's also conserved. Okay? So conservation momentum allows complex collision problems to be solved without knowing about the forces involved. The same thing was sort of true about the energy, except energy was so hard to account for all the pieces. Collisions, momentum, it's pretty easy to do that. Okay? Information about the average force can also be derived, but it's not usually known. It's usually derived. So let's get the definition for momentum. There are actually two types of momentum. One is linear momentum, the other is angular momentum. We're going to focus on linear momentum. So the linear momentum, and it's given the symbol P. I do not know why it's given that symbol P. Okay? My guess, I think the guy who first talked about it, and he didn't even use the term momentum. He called it his quantity of motion. That was Isaac Newton. When he was doing his principles of motion, the laws of motion, all that kind of stuff, he talked in terms of the quantity of motion, which he defined to be the mass times the velocity. That is what he called that. And since he wrote in Latin, I'm guessing the name he gave for whatever that quantity of motion was, it must have started with a P or a rho or something. But anyway, he used a symbol. The P is a symbol. Notice what else about this momentum. What kind of letter is that as opposed to that? Bold. What kind of symbol does it have over it? An arrow. What does that intuit to you? It's a vector quantity. So momentum is a vector quantity. Mass, though, is a not bold, no symbol, scalar quantity. Mass is a scalar quantity, but velocity is also a vector quantity. So a scalar times a vector is indeed a scalar, is indeed a vector. Okay, so it produces a vector quantity momentum. So it's the product of mass times velocity. What Newton called his quantity of motion is momentum. Mass times velocity. Vector quantity meaning the direction is important as well as the magnitude. Now the SI units for this are, what's the unit for mass? Kilogram. Velocity? Meter per second. So it's a kilogram meter per second. Now, for what it's worth, which is very little, in my mind, I don't see why they didn't name this a Newton. Okay? Because this was the unit Newton talked about all the time. The quantity of motion, mass times velocity, it would seem like that should have been named the Newton, but no, they named the force after it. Well, guess what? Back then, they had trouble separating forces and energies and momentum and all this stuff. I think they just got it wrong. But it's been named that, so it stays that. We do not have a name for momentum. It's a kilogram meter per second. We will, before the chapter is over, come up with another name, but it means the same thing. Okay? So vector quantity, as we've already mentioned, is the direction of the momentum is in the same direction as the velocity. Now, it's the same as the velocity's direction. So go and say, why did they put a apostrophe there? But that's as the velocity's direction. Okay. Because it's a vector quantity, you deal with the components of it. The momentum in the x direction is the mass times velocity component in the x direction. Momentum in the y direction is the mass times the component of the velocity in the y direction. And this applies to two-dimensional motion. If you had three-dimensional motion, you also have a z component for each of those. Now, this is a very little used formula, but it is correct. Momentum is related to kinetic energy. Now, if you think about it, they have a lot in common. They both depend on mass and velocity, right? What's the formula for kinetic energy? 1/2 mass, velocity squared. 1/2 mv squared, momentum, mass times velocity. That's simple. So they both can depend on the same two quantities, mass and velocity. Differences are kinetic energy, as all energy, is a scalar quantity. Momentum is a vector quantity. Okay? But since they're so closely related, let's see what we can do. Okay? Let me get my pen activated. The right color. And we have the kinetic energy. Someone tell me what that was again? Formula? Kinetic energy. 1/2 mv squared. Okay? And momentum? Now, I'm going to write it correctly. What is momentum? Mass times velocity. Now, I'm going to forget about the vectors for a moment because kinetic energy is not a vector quantity. And here's why. Because when you multiply two vectors together, if they're going in the same direction, you get a scalar. It's called a dot product. So that's what we're going to do, is multiply these two together. So what if you have p squared? Now it's a scalar quantity because certainly momentum is in the same direction as itself. That would be m squared times v squared. And the velocity is in the same direction as well. In fact, that's why this is a scalar quantity, because the velocity is in the same direction as itself. Well, to get from here to there, you're going to have to divide. This has a 1/2, so let's divide this by, let's see how to think of doing that. Here's how, let's do a mv, that's momentum, and multiply that by another v, that's v, okay, and multiply by 1/2, okay, and P is equal to mv again. Let's do it again. Let's divide both sides by m, and that gives you v is equal to p over m. So instead of v here, we put p over m, and sure enough, you have p squared over 2m. So that's how you get that formula. And again, it's not one I can ever remember using in a problem. Probably I have, but it's just not that common of a formula, but they like to present it to you. It's absolutely true. Let's see if the units work. What's the unit of momentum? Unit of momentum? Second? Kilogram, meter per second. When you square that, you get a kilogram squared, meter squared per second squared, divided by 2m. That's a meter. Divide that out, and you get, I'm sorry, this is mass, not meters. Divide out the kilogram, or one of the kilograms, Let me start this over. It's getting so messy. Okay. All right. Start that over. Okay. Divide by a kilogram. This is in kilograms. And your kilogram goes out, and you have meters squared per second squared. Okay. No, okay, I'm sorry. You had kilograms squared, so only one of those goes out. I had it right the first time. Just one of them goes out. Okay. What are you left with? Kilogram meters squared per second squared. That is a joule. Okay. So yeah, the units work. Now, what in the world do we mean by impulse? Now, if you think about Newton's second law, his most famous law, perhaps, what's the formula that sort of sums up? F equal ma, exactly. I'm not sure that Newton ever wrote that as that, F equal ma. That's what we use all the time, and it's certainly correct, and it summarizes his second law, but he didn't talk about, as far as I know, I don't read Latin, so I don't know what he said exactly, but he didn't talk about accelerations. He talked about that quantity of motion. Okay? And this is where I paused earlier today when I said, when you have a quantity of motion, mass times velocity, guess what the next thing he did with it? Time rate of change. The time rate of change of the quantity of motion, remember, was momentum, mass times velocity, and when you do the time rate of change of this over this, what do you have? Mass times, what's change of velocity over change of time? Change of velocity over change of time. Acceleration. So this is your force. I bet you that's how Newton talked about force, as the time rate of change of momentum. That's exactly what it is. Force is the time rate of change of momentum. Okay? So your change of momentum per unit time is your net force. We said as long as the net force is not changed, I bet you his law is read so simply. That first law says an object maintains its time rate of change of momentum, of quantity of motion, unless it's acted on by some net force. Because that's exactly right. If the net force is zero, it's not changing its time rate of change of momentum. In other words, its velocity, its acceleration is zero. Okay? Now, second law, force equal ma, force equal time rate of change of quantity of motion. There it is. It's just so simple. And like I said, it gives an alternate statement of Newton's second law. I bet you that's how Newton said it. Okay? It's also valid when the forces are not constant. When we're using that one, we assume the forces are constant. When you use the time rate of change of momentum, they don't have to be constant. They can be variable forces. So it's a much more general explanation. But what does that have to do with impulse? Okay? Well, what an impulse is, and by the way, let's take this formula right here. Delta P over delta T is equal to net force. Let's multiply both sides of that by delta T. And what do you have? Change of momentum is equal to net force times the time interval. Okay? Change of momentum is equal to net force times the time interval. All right. Let's think of some examples of that. And by the way, change of momentum, that's what impulse is. Okay? They haven't said it yet. I think it'll be the next slide, but that's what they're going to change. Change of momentum. Now, this gives us a new unit, I said we're going to get to it, for momentum. What would that be? What's the net force measured in? Named after Sir Isaac Newton. Time interval? Second. A Newton second is a momentum. It's a unit for momentum. So it can be a kilogram meter per second or a Newton second. Either one. Okay? And this also defines what an impulse is. Okay. Let's take a few simple examples. Are you just wear golf hats, or are you also a golfer?
I golf.
You golf. Okay.
Both.
What's that?
Do both.
You do both. Okay. You wear golf hats and you golf. Okay, good. All right. Now, if you're trying to drive the ball down the fairway, what kind of club do you use?
Driver.
A driver. Oh, clever. Okay. And how does the driver differ from, say, a sand wedge?
It has a lower loft, so it has a lower loft, but it's also just a different club. Like,
Okay.
the lower loft makes it we can swing it faster because of the
Okay. Swinging it faster.
just design of it.
Why? Number one, it's a longer club, isn't it? Aren't your drivers pretty
Yeah.
long and your sand wedge is fairly short, right?
Yeah.
Your putter is probably very short. Okay, now some people have those others out. You use that. Okay. All right. So, but the thing is, let's think about this. Your driver, which you're swinging, giving a good backswing, right? You drive through the ball and you try to maintain contact with the ball as long as possible, right? Okay? So, what are you doing there? You're giving more velocity on the front end before it hits the ball, to maintain contact with the ball for the most time that you can. Your force, which is greater because of that longer swing, the longer radius there, time interval greater, you give it a lot more change of momentum. Whereas a putter, typically what do you do with a putter? You don't hold it against it very long at all, unless it's going to be a long putt, and then you may leave it on there a little bit longer. So again, force times the time interval is going to do a change of momentum. So same thing true with baseball. Any of you play baseball ever in your life? Okay. If you played baseball, now I don't know about softball if they allow it there, but in baseball, you can either swing for the bleachers, which again, they crank it back here, swing through the ball, maintain contact as long as possible, force times the time interval. That gives you the momentum of that ball. Whereas sometimes if you're just trying to advance the runner, what might you do? Bunt. Now how do you bunt? You have minimum contact with the ball, and you actually, when you touch it, you pull back, so the force is very small too. That gives a very small change of momentum. Okay? Have any of you been watching Wimbledon this week? Okay, Wimbledon. Boy, when they go back there and swat that ball, and if you've ever seen a picture of this, when that tennis racket is in contact with the ball, the tennis racket deforms this way, the ball flattens out, and then they follow through, giving it a break. Whereas if they're going to do a drop shot, what do? Just barely get it over the net. The time interval much shorter, and the force much less. You do it all the time, right? That's what impulse is. A product of the force, applied force, times the time interval over which it acts. I think we've just run out of time, haven't we? So here's the continuation of this. When a single constant force acts on an object, there is an impulse delivered to the object. The impulse is your force times the time interval. Impulse also is a vector quantity because force is a vector quantity. Time, of course, is scalar. Okay? I is defined as the impulse. It's also the change of momentum. Okay? So that's the other way we'd say it. It's a vector quantity. Direction is in the same direction as the force. The SI unit for impulse is, guess what? Kilogram meter per second. Same as momentum. Also, it could be called a Newton second. So either one of those units would work. There are several other Okay. Let's stop now. Where we'll start next time is Quick Quiz 6.1. And what I'll do also is we'll come back to these slides on impulse because there are a few other examples I think will be worthwhile to do. So I'm going to put this on pause. I think you see the words and can read the first page. And one thing of interest here, when you're talking about the distance traveled, we're only talking about vertical distance. Only vertical, not linear distance or anything else, vertical distance. Okay? And the formula for power is here. Hey, Matt. Okay. The procedure, we're going to slightly change this, not too badly. It says teams of 2 volunteers. Y'all are teams of 4 volunteers each, okay? So if all 4 of you want to do it, allow them to do it. You'll just need to write somewhere, say you got room for volunteer 1, volunteer B, A and B. C can be in this margin, D can be in that margin, okay? If you all 4 want to do it, okay? But your teams of 4 volunteers, and you'll measure the work done, the rate at which it's done, and the horsepower rating as you move up a stairwell. Okay, one of you will be person A, then B, then C, and D if you choose to do all of them. You don't have to, but now does anyone have a reason you really don't want to walk or run the stairs? You do? You what? Oh, okay. So on your team, you'll be one that doesn't have to. So get at least 2 volunteers, and if 3 or 4 can do it, fine. Okay, now, okay. The first thing you're going to measure is the vertical height of the stairs. Okay, so let me bum a meter stick. Okay, you're on this team. We're going to do this not with the meter side, but with the foot side. So turn it so the zero's on the base. Okay, now I want someone to go up to the level above. Maybe someone in that team. One of you want to go upstairs? Yeah. Yeah. One person go upstairs. Okay? Now, and come over to this wall right here. Okay. Now what you're going to do is measure 3 feet. Okay, you see where that is? Okay, then if you'll lift that and put the bottom of that on my finger. Lift the meter stick. Okay. All the way up, all the way up, all the way up. Okay, on top of my finger. Okay. Straighten it up some. Hold it in place. Can you hold it? That would be 3 feet. There's 6 feet. Okay. It's right about the middle of this block. So then what I would do is come to the middle of this block over here till you get right here and go up another 3 feet. Okay. That would be about the middle of that block. And then go up another. Now, Courtney's up there at the top. Where is the floor?
Right here.
About here?
Yep.
Okay. So that's where you're going to measure from. The floor here to the floor there, and you have to scoot over a block. Measure to the nearest number of feet. Not meters, not inches, feet. Okay? Because guess how we're going to measure our work? What units? Foot-pounds. Okay? So you need that in feet. So the nearest number of feet. So everybody sees how you're going to do that. Okay? Measuring 36 inches being 3 feet, and just keep doing 36 up until you get to the person up there. Estimate where the floor is there, and that's where you stop. Okay? Nearest number of feet to the top. Okay? So I'll let you hand it to one of those in that group. That's their meter stick. Okay, so that's the first thing you're going to do, and you record that on the data page. Okay? Now, there was one other thing you have to record first, and how honest or dishonest you are with this, it doesn't matter to me. Just put down some number of pounds that either you weigh or you wish you weighed or whatever. Okay? So put down your weight in pounds. That's your force, right? And then the vertical number of feet that you go up. Now, in the instructions here, it says measure each step and multiply them by. That's so much error and increase involved there. you do a careful job measuring like this, you get the average number of feet. Okay? Okay? Now, here's next. Who has a stopwatch from group 1? Yeah, but you're the other group. You have the stopwatch?
No.
Oh, y'all didn't get a stopwatch. Oh, yeah, okay. Pull that out. I'll take the box and the plastic. Okay? Well, in fact, I'll take it all right now. Okay. Now, all the stopwatches, whether you have this one or the other, start is about 1 or 2 o'clock. Stop is there. That was 1.53 seconds. That's what that was, 1.53 seconds. Reset is over here around 10 o'clock. That goes back to 0. Okay? Now, normally you wouldn't be doing this. I'm going to do it for myself. I'm going to walk the stairs, and the very moment that I step on the first step, I start the clock. Okay? Now, I would keep on walking, and that would have been 8.91 seconds. Now, I didn't get but halfway up with that, so that's not a reasonable time. The timer is going to be up here, okay, where I'm standing. I'm going to clear that, and when the person starts to step on that first step, as soon as he starts moving, he or she starts moving, you start it, and you keep it running. Whoops. Start it. Start it. And you keep it running until their foot hits the top step, then you stop it. And then you record the time in seconds. Okay? All right. The next thing you do is go run the steps. Everybody listen to this. I do not want you running the stairs as fast as you possibly can. No way. I want you running the stairs as fast as you safely can. I don't want anyone falling. I don't want any split lips, split heads, broken bones. I don't want to fill out an incident report. Run it at something faster than a walk, but do it at a fast pace. Okay? That's not running the fastest possible. The fastest safely possible. Okay? And you'll do the same, start, stop, and do that. So you do that for each of your volunteers, if it's 2 of you, 3 of you, or 4 of you. Okay? I hope I'm still recording. Suddenly that got to PowerPoint help, which I don't want. I don't want this. I don't know why that's up there, but anyway. Okay, any questions on the time then? Everybody who walks it will also run it. So any who can't run it, don't walk it, okay? And get your measurements and record them on the back. Your weight, the vertical height of the stairs, the time to walk, and the time to run. Okay? At that point, you can come back to the classroom, because all the rest are calculations. Okay? Now, the first group, I'm going to leave here. You measure your height first, and as soon as you finish the height, set the meter stick over in the corner there, and I'll come get it for the fourth group, because we only have 3 meter sticks. So first group is going to be here. This is your clock. And the person whose timer is here, the person who's walking and running there, then you can rotate that around if you want to. Any questions from group 1? Okay. Group 2, come with me. Group 3 and 4, I'll show you where to go. Okay. Have we added any new people? You've come since, okay, both of you come. It's Raven and Bria. Okay. So you'll need to be in one of these 4 groups. Okay? Okay, oh yeah. Here I've got one. I'll have to go to the office and get the other one. Okay? Okay. Group 2, and all the rest of the groups come with me. 3 and 4, stop right here at the exit sign. I'll be right back. Okay? So come here, group 2. There's 4 or 5 of you. 4? One of you in group 2? Okay. Just one in group 2. The rest of you stay there. I'll be right back. You're group 1, aren't you? Huh? Okay. Who's in the stairwell? Okay, and they're taking their measurement. Okay. So This group said they're group 2. Y'all wait right there. I'll take a group of 4 or 5 here. 1, 2, 3. Are you in this group or not? Okay, you're in this group? Come on. Okay. Here's where you go. And again, you'll measure. The first thing you measure is the height in feet, not in meters or inches or anything else, in feet, from this floor to the top. So send somebody up there to receive. Someone start measuring off from the bottom here, 3 feet, 6 feet, 9 feet, and on up until you get to the top. So one person go up top and leave the stick down here, okay, and start doing that. Any questions on where to proceed from there? Any questions? Any questions? Okay. I'll be back in just a few minutes. Do you need a copy of the lab? Oh, you got it. She does. Okay, I'll get her one. Okay, I'll be back in a few minutes to see how you do it. Start with the meter stick and then all the way to the top. Yeah. From here to the top, not from the bottom to the top, from here to the top. What's that? Yeah, feet going up to the nearest foot. Okay. Groups 3 and 4, or whatever you want to number yourself, there should be 9 of you. Come here, okay? Are there 9? 1, 2, 3, 4, 5, 6. Okay, we lost somebody. 1, 2, 3, 4, 5, 6, 7, 8. Before she came, there were 4 and 4. Did y'all lose one? Oh, in the restroom. Okay, that's where it is. So both of your groups come home. Okay? Okay, take her right here and stop at the first stairwell. Okay, take her right at the first stairwell there, the exit sign. Right here. Okay. Okay, now one of your groups have a meter stick, right? Okay. The other group to come and watch. Okay. So where you're measuring from is the bottom down there to the top up there. So one person get up there, the other down here, and work your way up. Measure first the height in feet, closest number of feet from the floor to floor. Okay. Everybody understood? Okay. You each got a stopwatch too, right? Okay, how many are in your group? 4 or 5? 4? So that leaves the last group with 5, right? Okay. I'll get y'all started, but I've got to go get you a meter stick. Okay, so y'all come on. The other 5 of you come on. Y'all got a stopwatch, right? Okay. Someone has it. Good. Okay, this will. Oh, okay. This is your stairwell. You'll be going from the bottom there to the top there. So y'all can go on and get started on your times, and as soon as I get a meter stick, you can do the distance. But use that wall there to estimate your distance. And be sure you have someone at the top estimating what the floor level is. Hey, I just saw Matt. Okay, so y'all must be invading. Okay, so you got 5 people or 4? Where's the 5th one? I keep losing people. Okay. Oh, it may have. Okay. Well, then y'all can start doing your timing. I would say the timer stands here so you can see starting and stopping time. Okay? I'll go get you a meter stick, and the other person needs a lab. Okay. So one team decided to measure the height in inches and then round that to the nearest number of feet, but that's up to them. Okay, the teams, when you did your measurements, you should have the entire back of the page filled out. As someone pointed out, time for running is blank where you walked, and time for walking is blank where you ran. But everywhere there's a blank line there, not a blank square, but a line, you should have a number in there. Any questions about what those numbers should be? Everybody see it and understand it? Then once you filled out those, then you go back to pages 126 and 127 and you answer questions 1 through 5. Okay? Is there any problems on any of those? Any questions, any clarifications? Okay? A lot of times some people have some questions on some of them, what are they meaning? But have y'all got them all? Okay. If you've gotten those done, then I've got your test 5, and anyone who wants to test 5, whether you want it or not, you're going to get it. Okay, you got yours already. Did you get yours already? You did? Okay. Did I give y'all a lab before for this one? Now, I probably gave you a different lab because I didn't have this one handy. I just decided to do this one instead. A little bit more. It said energy was the name of the lab. It was a one page. Oh, I thought y'all asked for it before you left. Did you get one? Okay. Did you get one? Y'all get one? Anyone behind you there? I see books. Anyone behind you? One past one. Yeah. I'm sorry. I don't want a string of 15 digits, okay? So I'd rather have significant digits, but that's one. In fact, that's one. One more over there. Take one past 2. Okay, let's look at the question of significant digits. That's a good question. Okay? Now, this would be a tough one. I said measure, okay. I want you to estimate your weight, and I would guess you can do that to the nearest 3 digits, can't you? Okay. If you get any more precise than that, that's fine. But if you know it to approximately 3 digits, okay. Vertical height in steps and feet, hopefully you can get that within 2 digits, okay. But if you can get 3, that's fine too. The time, I know your stopwatches usually gave you 3 digits there, right? So you got 3 digits there for both times. The work done, I would say give me either 2 or 3 digits there, but you're probably going to have a big number, right? Your weight times your distance, that's going to be a pretty big number. So however many digits you got there, but stop at the decimal point, okay? It won't be more than 4 digits. Power, divide that by your time, round that to either 2 or 3 digits. Usually 3 digits are fine. And then horsepower, when you divide the power by 550, again round to 3 digits. 3 digits should be fine on all those. Maybe your vertical height's only good to 2, but we'll let you get by with 3. The work done, probably you'll have 4 digits there. But don't give me a bunch of decimals. Round it. Does that make sense? Okay. And when you have your questions answered, and have your labs turned in, you can certainly go. Everybody got
We're good for just 2 significant digits on the,
what's that?
so we're just good for 2 significant digits on the vertical height.
If that's all you got, that's fine.
And work is good before.
Well, work, yeah, you got 4 digits before the decimal, so put all those down. But then the others round to 3. Have you actually been to the Masters? You just ran the count.
My best friend worked. I'm working at night shift, but my best friend worked at it last year, so he gave me
Oh,
the
really?
stuff in his area.
Yeah.
But it's on my bucket list. I was
Wait.
going to go to a practice round, but ended up not being able to because I couldn't find anybody to go.
Yeah. We have a house in Burke County, Georgia, which is just south of Richmond County.
Really?
And last year, 2 sets of nieces and nephews, I get a boat out this one, came and they stayed the first 2 days, practice round, the next group came in for the next 2 days. They had 4 people each.
My best friend, he His parents were divorced, and his mom lives in Hoover, and he lived with him in high school. His dad lives in all that
So
stuff.
on that one, then I have the significant things up there because I got nervous.
Oh, okay, that's fine. Thanks. I grew up just south of Augusta most of my life, so I've never been on the course. I've never been in that Augusta National Golf Course. It's quite a place out here.
Yeah, it's my bucket list to be there.
Yeah.
Appreciate it.
All righty. Okay, if there are no more questions, I'm going